Today we're going to use our complex analysis to look at Euler's identity. So we start by defining a function of theta, where theta is an angle in radians, as cosine theta plus I sine theta. Now you'll recognise this as the rectangular coordinates of a complex number, nothing more. First step is to take the derivative with respect to theta. So derivative of cos theta is negative sine theta, and the derivative of sine theta is cos theta, so I is a constant times cosine theta. Now recognising that negative 1 is I squared, we have I squared sine theta plus I cosine theta. Taking a common factor of I, and then I'll write these terms in the reverse order, so cosine theta first plus I sine theta. F dash theta, the derivative of our original function, turns out to be I multiplied by this is our original function. F dash theta over F theta would equal I. Those of you who've done some integration will recognise that we could integrate both sides of this equation with respect to theta. Now the integral of an expression like this, where it's a derivative of a function divided by the original function, is ln, the natural log of that function. The integral of a constant is I multiplied by theta plus a constant of integration. Now writing this instead of using log format but using exponent format, I would have e to the power of I theta plus c, the constant of integration, would equal the original function, which I'll write as cosine theta plus I sine theta, just writing it out from our original definition. Now the constant of integration. We need to evaluate this formula for some given value of theta that we know. We can choose. We will let theta equal 0 for convenience. Then this becomes 0 multiplied by I is 0, so this is just e to the power of c. Cosine of theta is cosine of 0, if we substitute, cosine of 0 is 1. The sine of 0 is 0, so this becomes disappears. We have e to the power c equals 1, and we know therefore that e must be to the power 0, so c therefore equals 0. Then rewriting our identity, e to the power of I theta, because c is nothing, equals cosine theta plus I sine theta. This is Euler's identity, and this we recognise as the rectangular coordinates of a complex number with a modulus or a length of 1, and this depends only on the argument, so this is the polar coordinate of the same number. We could represent this on an Argand diagram with a real axis and the imaginary axis. So here is a complex number with a length of 1, argument of theta, and we would have, here is the cosine theta part, here is the I sine theta part, the rectangular coordinates, and this would apply anywhere around the unit circle, only dependent on the argument theta in radians. We'll see more of this in the next video.